All righty, guys. Well, you have been the stalwart, most persistent members of the class, showing up all the way here to the very last day. All right, so just a couple of procedural things. Last time we were together, we talked a little bit about the final, and I wrote it down, and I don't remember where I put that sheet of paper. Here it is. So this will be your reminder. I will adjust put something on the syllabus pages and on Canvas just to remind people who aren't here. But we said that we would start the exam on Wednesday morning. I'll get some exam questions out to you guys on Wednesday morning, the 13th, and they will be due at the end of the day on Friday, the 15th. So you have pretty much 3 full days to work on them. And then in addition, I've got office hours scheduled now for from 11 to 1 on this coming Monday. I mean, I'll have office hours again today after class if you want to meet me then. Otherwise, either make contact with me through email or just show up on Monday. So anything that I need to say about that, those last parts of the course? All right, that gives us 1 day left today, and I tried to think about the best way that we can use this time, and I don't know to what extent you guys wanted to review the entire semester in 1 day, which I'm willing to do, and instead to what extent you wanted to hear about the other topics in number theory. So our semester got cut a little bit short, and we couldn't quite do all the topics that I wanted to get to. And besides that, even when we can get to all the topics that I put into the syllabus, that's not all the topics that I really want to get to because number theory is a very broad subject. And so what I thought I could do today after we finish what review you guys want is I can take you on a little tour of the other topics in number theory. So those are my the only things I have on the agenda today. Do you guys have anything else that you wanted to talk about besides reviewing the course we've had and talking about the other subjects within number theory?
Real quick, I wondered what are the sections exactly again that's like the new material after the second exam that will be on the final?
Good question. So I have the textbook in front of me. So since the last exam, what have we added? We already had the multiplicative functions and even what we did about cryptography, that was on the previous exam. So since the exam, all we've added were all the topics in chapter 9 on primitive roots. Certainly the idea of order, the existence of primitive roots when they do exist and when they don't. And we talked about discrete logarithms and index. So the first 4 sections of chapter 9, I would say we worked on all of those. And then I guess we switched straight into quadratic residues in chapter 11. And mostly, I would only hold you responsible for sections 11.1 and 11.2. So it hasn't been that long since the exam, but I would add those 6 sections to the list of topics we had on the previous test. And the final is cumulative, so that also goes all the way back to chapter 1, which I hope you guys would consider pretty easy at this point. It took us a while even to get to things like modular arithmetic, but certainly the topics involving the division algorithm, the Bézout lemma, all the facts about GCDs, certainly everything leading up to the fundamental theorem of arithmetic. Those are all topics that we did a long time ago, and I assume you guys are pretty familiar with them right now, but you might want to look back at the details of those topics.
Do you think, will you say the tested material would be focused more on the new stuff or evenly spread out through the semester?
You know, nominally, when I write a final exam, I try to make it evenly spaced. So it's a little different for an upper division class like this, but even for number theory, I'll do something like what I do for the calculus classes, which is I write one question from every single section that we covered. And then of course, that's way too many questions. And so I throw some of them out and then just give you the rest. And I try to make it more or less evenly balanced, but you know, especially a class like this where the level of the material that we've been studying has gone steadily up during the semester, it feels almost a little insulting to ask you a question about the commutative property of addition or something. But I might. So yeah, I'll try to make it I'll try to find interesting questions from the early part of the semester. The most, how should I put it, the least trivial kinds of things that I could imagine asking you about the early material when we were just establishing the nature of the set of natural numbers or the set of integers. The way I tried to make it seem non-trivial was to ask you to compare to other number systems where you didn't have some of the features that the integers have or that the natural numbers have. And so I did introduce you guys to the Gaussian integers, for example, just as a way to say, well, you know, is it obvious that you can do this, that, or the other thing? Try to see if you could do the comparable thing with the Gaussian integers. And the Gaussian integers actually are about as close as you can possibly get to the ordinary integers. They have basically all the same properties, except for the ordering. On the other hand, we also did look at those, what are called rings, where I asked you to look at numbers, complex numbers of the form a plus b times the square root of something. And where the a and b are restricted to being integers, then that becomes a set where you can add, subtract, and multiply, and you can ask when is it possible to divide, you know, what divides what. And for those things, we did discover that even some things that we've always taken for granted, like the fundamental theorem of arithmetic, they're not always there. So I guess I could ask you questions from early in the semester that would be about those things. We never really did study those rings in great detail. I mean, I never went through all the steps of proving the fundamental theorem of arithmetic does hold for the Gaussian integers. Although I indicated, you know, that when we did prove it for the ordinary integers, I said, hey, look, all you really need is to know that the division algorithm holds. And, well, the division algorithm does work for Gaussian integers. So did I answer your question? I mean, I will try to give you questions from all the parts of the semester. But some of the material at the very beginning just seems kind of lame. You know, the definition of what makes a prime number. So I'm not sure if I fully answered your question, but.
Oh, that's good. Thank you.
Yeah, okay. Other questions, sort of general questions?
Hey, yeah, speaking of like different number systems and stuff, how deep are we going to go into Gaussian integers?
Well, I've been sprinkling little facts along the way whenever I thought I could. So, for example, we have now decided that if you had a number which was, how should I put it? If you have an ordinary integer, you can think about it as being an ordinary integer or a Gaussian integer, you know, a plus 0i. And, well, if it's composite in the sense of ordinary integers, then it certainly is composite as a Gaussian integer. If it's prime, when you view it as an ordinary integer, we notice that sometimes that number stays prime, like 3 plus 0i is a prime among the Gaussian integers, but other ordinary primes like 5 are no longer prime in the Gaussian integers because 5 could be written as 2 plus I times 2 minus I. Well, if you think about it, when you ask which primes stay prime in the Gaussian integers, that's exactly asking which primes can be written as a sum of two squares, which is a question that we addressed after we got through all the business of quadratic residues, and in which circumstances is -1 a square mod p. And so you now know that the primes that stay prime are precisely the ones that are 1 less than a multiple of 4. So, so you have an understanding now of really how the Gaussian integers work. There are primes, and there are composites, and there are units. We know the only units are plus or minus 1 and plus or minus I.
Right.
And I've indicated a few times, and you can find a proof in the book actually, that you can make the division algorithm work. You just try your best to get a remainder at each stage that's smaller than your divisor, and smaller meaning that it's closer to the origin in the complex number plane. And then the division algorithm works, and so the rest of the proof of the fundamental theorem of arithmetic works. So every number can be written in a unique way as a product of Gaussian primes. Every Gaussian integer can be written in a unique way as a product of Gaussian primes. So I'm not sure if I really answered your question, but yes, basically everything you could ask about the Gaussian integers at this point, you actually have the tools of answering your own question.
Okay.
I mean, let me ask you this. Here's a sample. Do you suppose that there are infinitely many Gaussian primes? We know that there's infinitely many ordinary primes, so can you make the proof work for the Gaussian integers? And there's a few ways that you could address that. One thing you could say is, well, you could say to me, you could say, well, you've already assured us that any ordinary integer that's 1 less than a multiple of 4 continues to be a prime when viewed as a Gaussian integer. So you will for sure have a win if you can guarantee for me that there are infinitely many primes that are 1 less than a multiple of 4. And it turns out that there are, and I don't think we've actually discussed that fact. It's a little tricky, but not too hard to prove this for the modulus of 4. But there are infinitely many primes that are 1 more than a multiple of 4, and there are infinitely many that are 1 less than a multiple of 4. And broadly speaking, there are about as many in each camp as you might expect. I will tell you that that's a famous theorem, is that if you give me any arithmetic progression, any stuff they call it arithmetic sequence, like 1, 5, 9, 13, 17, any arithmetic progression has infinitely many primes in it, as long as the common difference, the 4 in this case, is relatively prime to the first entry in your sequence. So there's infinitely many primes of the form 4n plus 1, and there's infinitely many primes of the form 4n plus 3. There's not infinitely many primes in the form 4n plus 2, and I think you can see why. Anyway, that would be one way to show that there's infinitely many Gaussian primes. Does anybody want to propose another method that you think you could prove it? I got one for you. You could just list.
We could suppose there are finitely many of them, and then maybe we could generate one from this finite set.
Okay, so this would be something that you could try. And of course, you have to watch out for the details of making sure that the proof actually works, because don't forget, a lot of our proofs that we wrote down for ordinary integers, we sometimes would be relying on the less than property. You can still talk about Gaussian primes as being larger or smaller, but you have to be making a reference to their magnitude. And that's not quite the same as larger or smaller. In particular, you can have different Gaussian integers that have the same magnitude. But yes, so something like what he just proposed might work. If you thought there were finitely many primes, just multiply them all together and then add 1. And now you have something that's not, it's not a multiple of any of the primes, because when you divide it by any other existing prime, then you'll have a remainder of 1 left over. Of course, you do have to convince me that 1 itself is not a multiple of any prime, but that just takes a minute. You also have to worry about one tiny little issue, which is when in the ordinary integers, when you multiply all the, supposedly you have a finite list of primes, when you multiply them all together and then you add 1, you knew you had a very big number. When you multiply some Gaussian numbers together and add 1, you could get 0. And 0 actually is a multiple of every prime, every integer anywhere. And so that's something that's the kind of little twist that makes your life a little bit more difficult when you're working with the Gaussian integers, is you've lost this idea that multiplying things automatically makes them bigger. So, I mean, that proof almost works, but you have to be just a little bit careful. Here's another proof that you could give. You could say, well, I don't know, maybe there's only finitely many primes of the form 4n minus 1. So we can't use that argument. Okay, it turns out there are such infinitely many such primes. But even if there weren't, you still know that there's infinitely many ordinary primes. So, okay, maybe you thought it was true that all the remaining primes past a certain point were all congruent to 1 modulo 4. And in the ring of Gaussian integers, those things are not prime anymore. But even though they're not prime, they can still be factored as Gaussian primes. And here's the thing, if you look at the Gaussian primes that divide 17 and the Gaussian primes that divide 29, the fact that 17 and 29 have no common divisor in the ring of ordinary integers means that they don't have any common divisor in the ring of Gaussian integers either. And the reasoning is simple. I guess I should turn the camera around and write this, but I'll let you just imagine this. Since you know that 17 and 29 are, of course, they're both different primes, but in particular, they're relatively prime to each other. So by the zoo lemma, you could find a couple of ordinary integers to multiply them by, so that 17 times this plus 29 times that adds up to 1. Now take that equation and view it as an equation involving the Gaussian integers. If you thought that you had any prime divisor of 17 that also divided 29, I mean Gaussian primes, well then that prime would divide the entire left-hand side of this equation. And so it would have to divide 1. And that's a contradiction. So the conclusion is, sure, the numbers 17 and 29 and so on, they're not prime in the Gaussian integers anymore, but they're at least still coprime. And so when you list the prime divisors that they have in the ring of Gaussian integers, well, every ordinary prime is going to make its own new Gaussian primes. So when you assemble the Gaussian primes, you get actually 2 new ones for 17 and 2 new ones for 29 and so on down the chain. So that'll give you infinitely many Gaussian primes. So the Gaussian primes are fun to play with, except that the answers keep coming out really pretty much the same as they are for the ring of ordinary integers. The more interesting things start to happen when you look at, well, basically, you get more interesting material in 2 ways. One is, in some of these rings, you lose unique factorization, and I've given you guys examples of that. And another thing that happens is that in some of these rings, you pick up a lot of units. So in the Gaussian integers, there are 4 units, plus or minus 1 and plus or minus I. Oh, maybe I should ask somebody to remind us, what is the definition of a unit?
Does it have an inverse?
A unit is something that has an inverse. So if you're in a ring, that means you're in a place where you can do addition, subtraction, and multiplication, but you can't necessarily do division because not everything is invertible. So when we've been working with the integers mod n, the invertible elements are sometimes just called units, but there are non-invertible elements, and you can't divide by 2 when you're working mod 6. It's not an invertible element. Okay, so in the ring of Gaussian integers, we have 4 invertible integers, 1 and minus 1, I and minus I. when you take the integers of the form a plus b times the square root of minus 3, the only units are the ones you already know about, 1 and minus 1. But let me write something down for you. Let's look at a different one of the rings of that type. I said I was going to talk to you guys about extensions and different parts of number theory. So just because of the way your questions have gone, you guys have sort of forced me into it. We're doing it. We're doing it now. So how about if I look at this ring, I'll take z adjoined with the square root of, I don't know, square root of 5. How's that? So what that means is it's just a set of all complex numbers. Well, in this case, they'll actually all be real numbers, but they're all the real numbers that you can write in this way, such that a and b come from the set of integers, ordinary integers. So this is a set of objects, a set of real numbers. You can add them and you'll get another one of this type. Subtract, even multiply, because if you multiply two of these things together, of course, a square root of 5 times the square root of 5 will give you an ordinary integer of 5. You can't always divide, but you can sort of tell when you will be able to find an inverse to one of these things and when you won't be able to. You see, that what always happens is if you give me any, can I call it alpha, that comes from this set, then I will talk about alpha bar as being exactly the same combination of a and b, but with a minus sign thrown in the middle. So this will also be an element of z bracket square root of 5. And the reason that I single it out is because when I multiply alpha and alpha bar together, I get an ordinary integer. In fact, it's, well, you guys know the factorization for the difference of two squares. I've just multiplied those two things together to get this one. And, well, if alpha had an inverse, call it beta, then alpha bar would also have an inverse, beta bar, which would exactly be found by putting the minus sign into the middle of the formula for beta. So then alpha and alpha bar would both be invertible, and so this would be an invertible element of this ring as well. But this one is an ordinary integer, so this would have to be an honest-to-God integer. And therefore, I have just observed that if alpha is a unit, then this a squared minus 5b squared would have to be equal to the ordinary, one of the two integers plus or minus 1. And that's actually an if and only if statement, because if I knew that this alpha bar came out to be a -1, for example, well, I would be able to see what an inverse is. If alpha times alpha bar was equal to -1, then an inverse for alpha would be, let's see, I would need negative alpha bar. So this is actually an if and only if statement. The inverses, the invertible elements of this ring are exactly the combinations with an A and a B in them. Wow, the shading is so bad. The combinations with an A and a B in them that happen to satisfy this equation. And I want to say something about the solutions of this equation, but before I do that, I want to use the kind of tools that you guys have already been working with to rule out a combination that's in here. Let's see, how do I want to do this? No, 5 wasn't a good choice. Never mind. All right, so let me think about the solutions to this this problem here. I'm pausing because I was going to have you guys show me that in fact there are no solutions to this equation which would ever give you a -1. And I thought for a second that was obvious, and then I realized I should have used a different number besides 5 to make that come out to be obvious. but now I'm not even so sure that it's true. In fact, yeah, in fact, if you look at 2 plus the square root of 5, and you multiply that by 2 minus the square root of 5, what you'll get is 2 squared minus 5, which is 4 minus 5, which is negative 1. So there's an example of an element of this set that does give you a norm equal to -1, so that's a unit, and its inverse would be the negative of this one. Of course, you can also make this quantity come out to be +1. The easy way to do that is just 1 plus square root of 5 times 1 minus 0 times the square root of 5. That's going to be a +1. So there's 2 examples of units inside this set. So, okay, let's pursue these units a little bit. So one of the things that I used a few minutes ago was the observation that if you multiply together 2 invertible elements, their product is also invertible. Namely, the inverse of a product is the product of the 2 inverses. So I could multiply these 2 things together and get another invertible element. Goodness, what was that?
Oh, my.
Well, in fact, that was a comment about boring, which right at this moment was appropriate because I just said, here's 2 invertible elements and their product is invertible. But of course, in this case, that's obvious because that's just the number 1, and 1 times anything is itself. So sure, that's invertible, but you get something non-trivial when you realize that this invertible element can be multiplied by itself to get another invertible element. Well, we've had that kind of observation in the past. When we looked at the integers mod n and we realized that some integers mod n are invertible and others are not, we realized that the collection of them was closed under multiplication. And in particular, you could take any single invertible element and start looking at its powers until you come back to the number 1. And as soon as you do, that determines the order of that invertible element, mod n. So let's try computing the order of this invertible element in this ring. Okay, well, here's the alpha to the first power, 2 plus the square root of 5. And now I'll get alpha squared. So that's the square of the first term, the square of the second term, and 2 times their product. So I'm up to 9 plus 4 root 5. Okay, how about alpha cubed? So now I have to multiply these 2 things together. So here's the integer parts, and here's the product of the non-integer parts. And then the other pairs are going to give me 8 root 5 and 9 root 5. So I have 20, I got 38 and 17 times the square root of 5. Well, after doing this a little bit, you start to realize these numbers are just getting bigger. The coefficients, the integer part and the non-integer part, those 2 integer coefficients are always going to be positive and increasing in magnitude. So in fact, this alpha has infinite order. That implies that you're actually going to have infinitely many units in this particular number ring here. So the other examples that we've looked at, where I had a negative number in this spot, we always had just a finite number of units. In fact, typically it's just 1 and -1. But when you have a positive number under the square root sign, you will actually get infinitely many units, if you have any at all. You take 1 and you start raising it to different powers, then you'll end up with infinitely many different units. So this is not a kind of an equation that's a symbol that I not once have written this whole semester. There's infinitely, the order of this unit is infinite. It's of infinite order. So for those of you who have started to look into group theory, what I'm saying in this case is that my group of units includes both elements of finite order, that's like the number -1 is an element of finite order, and then there can be infinite, this is an infinite cyclic component to that group. So it's a little different from some of the structures that we've seen this semester. Now, I've already mentioned that these 2 these two units come from solutions of this kind of an equation, you look at the remainder of these, they will also have to make this equation be true. You get a unit if and only if you have a solution to this problem. And I started off with a kind of an easy one, but then I started to get a few others that were not quite so obvious. 9 squared minus 5 times 4 squared, yeah, that's 81 minus 5/16, which is 80, and that leaves you with a plus 1. 38 squared, I don't even know what that one is in my head, times 5 times 289, so that will turn out to be, actually this one I know, this will come out to be a minus 1. In fact, the general pattern is that if you call this thing the norm of alpha, and I used that notation much earlier in the semester, then it's easy to check that the norm of a product is the product of the two norms. So norm is an example of a multiplicative function. You don't need to know that alpha and beta are co-prime. I don't even know quite what it means at this moment to say that alpha and beta are co-prime. But anyway, for any two integers, for any two elements of this set and two elements in this ring, we do have a multiplicative property. And so as soon as I show you that the norm of alpha for my first alpha, that norm was a -1, that tells me that all these others are going to switch back and forth between having a norm of -1 and a norm of +1, which means that if I take every other term in this, I end up with either a solution to this equation or a solution of this equation. So I end up with actually infinitely many in the two types. These are examples of what are called Diophantine equations. And that simply means that they are equations in multiple variables that are written down with polynomials. And the question that you ask is, what solutions can I find in integers, or I should actually say pairs of integers? And that opens up a whole big category of investigations in number theory. You ask yourself, when can I solve an equation in integers? And in the cases that I'm describing here, I have already demonstrated that I have infinitely many solutions, and in fact, I know a way that I can generate at least some of them. Have I got all of the solutions? That's not clear at this point. Is there a way that you can describe all of them? Also not entirely clear. So let me pause a little bit when we were discussing this particular number ring. And since I've introduced Diophantine equations, how about if we try a few others that are similar? How about if I ask you to solve this Diophantine problem? So this is the sort of thing that I was going to say earlier that I thought there was an easy proof I could have you guys do. So this is an equation I'd like you to solve for integers. That's a Diophantine problem. When I say solve, people can interpret this in a few ways. The most basic question is, do there exist solutions? The next question after that is, if there are solutions, are there infinitely many? And if the answer to that is a no, then the question would be, can you tell me how many there are? And if you can get that far, then I guess I would say, can you actually tell me what all of the solutions are? Can you give me a method for creating them, that sort of thing? Does anybody have any proposals? How can you decide whether or not this equation would have any solutions? Well, one question that you should ask is, I can't find any solutions among the integers if I can't even find any solutions among the real numbers. So can you find any solutions for this equation if A and B are allowed to be any real numbers? Oh, come on. Somebody should be able to find one. Give me a real number solution for this equation.
Square root 7 and 1.
Okay, yeah, square root of 7 and 1. I was going to go with square root of 2 and 0. In fact, there's infinitely many real solutions. In fact, this is just the kind of thing that you studied in high school. If you call these letters X and Y instead of A and B, then you know that the solution set in real numbers is the set of pairs of real numbers in the Cartesian plane that happen to lie on a certain hyperbola. Is that a hyperbola? Yeah, it goes like this. So the hyperbola x squared minus 5y squared equals 2, there's infinitely many real solutions. And that's trivial, but I do have to point out that that's a necessary condition if you want a polynomial equation to have an integer solution. Well, then it at least has to have a real solution, because every integer is also a real number. So if I had asked you to put a squared plus 5b squared equal to 2, then that would be easier to check, because I could use properties of the real numbers to say, wait, as soon as b is anything other than 0, this left-hand side is too big, and therefore b would have to be 0, but then a wouldn't be an integer. So one of the tests that people use to decide whether there are solutions is to see if there are real solutions, and if not, then the integer Diophantine problem had no solutions. Well, okay, so there are real solutions. Has anybody found an integer solution yet? A pair of integers with a squared minus 5b squared equals 2. Yeah, you're not going to find any. And you know why? Because if you had two integers a and b that made this equation be true, then it would also be true that a squared minus 5b squared would be congruent to 2 modulo n for any n. And so you suddenly realize that, wait a minute, I could test this kind of a congruence modulo different moduli and see if maybe one of them would already tell me that it's impossible to solve this kind of a problem. It's not immediately clear how that would help you. We have talked about whether or not, for example, 2 can be written as a square modulo n, or whether or not, what would that be? Negative 2/5 could be written as a square modulo n, right? So here you would be asking whether or not 2 and negative 5 are either both squares or both non-squares mod n, because that would tell you whether you could solve this equation. But we haven't had a quadratic equation with 2 variables in it before to try to decide whether it's solvable mod n. We have had linear equations in 2 variables, so we've solved things like this before, right? In fact, we've talked about how to solve linear equations in 2 variables in the ring of integers. But this combination of making the degree go up to 2 and making the number of variables go up to 2, that's something new for us. And it's a hard question to get started with, although it turns out in general the answer is it's pretty easy to decide. But I haven't even told you which n I'm interested in. And I have to tell you, there's one value of n which is of special importance, namely n equals 5. Because when you look at this congruence modulo 5, then you are literally asking me for the quadratic character of 2 modulo 5. So does there exist an integer a that makes this congruence be true? You have to look at the Legendre symbol of 2 modulo 5, and you know that we can compute that in one set of symbols like this. But 25 minus 1 is 24, divided by 8 is 3, and minus 1 to the 3rd power is a negative 1, which means that there is no solution to this congruence modulo 5. And if you can't even solve the congruence mod 5, you're not going to be able to solve it in integers. Stated back in the terminology that I had for this number ring, I guess what you've decided is that the number 2 cannot be written as a norm. No combination, no alpha in this set ever has a norm that's equal to 2. And actually, kind of what that tells you is that the number 2 is going to end up staying prime in this setting. In fact, I guess I'll just show you. That's obvious. if you thought that 2 could be written as a product of 2 elements in this ring, then that would imply that the norm of 2 would be the norm of beta times the norm of gamma. And the norm of 2 meaning 2 plus 0 times the square root of 5, the norm of 2 is just 2 squared minus 5 times 0 squared. So this is a 4. So since the norm of everything in this ring is an ordinary integer, these norms are going to have to be either plus or minus 1, plus or minus 2, or plus or minus 4. Well, they can't be plus or minus 2. I've already showed you that you'll never get a norm that's equal to 2. And in fact, the same reasoning will show you'll never get a norm equal to negative 2, because the quadratic character of negative 2 is also a negative 1. So what you're left with is that if you did think that you could write 2 as a product, then one of these two factors would have to have its norm equal to plus or minus 1. And if the norm of beta is plus or minus 1, that means that beta is a unit. So in fact, every attempt to write 2 as a product leaves one of those factors as a unit, and then the other one is, it's in the language of ring theory, we would say that gamma and 2 are associates to each other. They're really no different from each other as far as the factorizations go. So there's no way to write 2 as a product unless one of the two factors is a unit. So all of this goes to show, that the number 2 stays prime in this new ring. All right, so now let me go back to this thing about the units. Where did the units go? Here. So this is an example of a Diophantine problem that involves 2 variables, and it is just quadratic. In the case of a single quadratic polynomial, even in multiple variables, there is a theorem that says you can solve it, you can find solutions in integers as long as you don't run into any of the problems that I've already addressed. In other words, you can't hope to solve it with integers if you can't solve it in the set of real numbers. And you also can't hope to solve it in integers if you can't solve it mod n for every n. However, the interesting theorem says if you can solve it mod n for every n, and you can solve it in the ring of real numbers, then there are integers that make the equation be true as well. So that's a fairly deep theorem, but it can be very useful for quadratic Diophantine problems. The more general Diophantine problems, that result isn't true. I mean, in the forward direction, it's still true. If you can't solve it with real numbers, don't try to solve it with integers. Or if you can't solve it mod n for some n, then that means you can't solve it in integers. That part is still true, but being able to solve it mod n for every n doesn't guarantee that you can find a solution in integers, unfortunately. So let me introduce to you a couple of other Diophantine problems that people have looked at. The quadratic ones, as I say, there's some easy, not easy, but there are some useful theorems that make it possible to get a decision about what the solutions look like as long as the polynomial is quadratic. And that applies even when the number of variables is more than 2. So here's an example of a Diophantine problem. It's still quadratic, but I'll go up to 3 variables. Anybody seen that equation before? Yeah. So this is a theorem, an equation that has geometric interest. You know that this refers to if A, B, and C are the lengths of sides of a triangle, then the triangle is a right triangle if and only if this equation is satisfied. There are plenty of real numbers, triples of real numbers that satisfy this equation. Any solution in real numbers that makes this equation be true would be a point in three-dimensional space. If you call the coordinates x, y, and z instead of a, b, and c, it might be easier for you to visualize. The set of points in three-dimensional space where this equation is true happen to form a cone, a two-sided cone. So there's oodles of real solutions. And of course, the statement about the Pythagorean theorem, that has only to do with real numbers for a, b, and c. But people do like whole numbers. So it's reasonable to ask whether are there solutions of this in whole numbers? And I guess you guys have all seen this one. Oops, sorry, got ahead of myself there. So there's one solution at least. Let me just ask if you guys have seen any other integer solutions to this problem.
Infinitely, like if we have two consecutive integers that add up to an odd number, then we can choose the smallest side of the triangle as the square root of that sum. Like 5, 12, 13, and 7, 24, 25, and 9, 40, 41. And in that pattern.
Wait, so say again, if you have two numbers that add up to an odd number, so u
consecutive.
And consecutive.
And u plus 1.
Okay. And then you do what now?
And I can choose the smallest number to be the square root of their sum.
The square root of their sum is not necessarily a perfect square.
If it is perfect square. And
if it is a perfect square.
And there are infinitely many of them.
That's true. Yes, so there are, okay, so at least you know that there are more solutions. There are, in fact, infinitely many solutions. The fact that there are infinitely many is not really a surprise because you can do this. You could just you could scale the whole triangle up by some integer factor, and you can obviously have lots of solutions to the original problem, and yet they're not really interesting. I mean, what you are doing essentially is taking one point on this cone and just finding more solutions that are all along one single line that goes through the origin. So then the question is, okay, well, can you find any integer solutions that are not along that line? And the answer is yes. So one of the choices is you could have the 5, 12, 13 triangle. And I assure you, your high school geometry teacher used this one in some of his or her examples for you as well. So that's an example that's not simply a stretched out version of this one over here. In fact, this is an example of a Diophantine problem that has infinitely many sort of truly distinct solutions. I can even go a step further. I can tell you how to get all of the solutions of this Diophantine problem by playing around with some formulas. So if you take any two numbers u and v and look at the numbers u squared minus v squared on the one hand and 2uv on the other, then you know that if you square this quantity and square this quantity, you will actually get a perfect square, namely u squared plus v squared squared. And that applies to the problems here. I mean, if I take 2 and 1 from my u and v, then I'll get 3 and 4 and 5. And I get this one with, let's see, what do I need? 5 is 3 squared minus 2 squared. And 2 times 3 times 2 is 12. So 3 squared plus 2 squared is 13. So this gives you a parameterization of the sum of this, well, actually all of the solutions for this Pythagorean Diophantine problem. How about that? 2 ancient Greeks in one sentence. This Pythagorean Diophantine problem has infinitely many solutions that can all be parameterized by formulas like this. Now, the situation with Diophantine problems is once you start realizing that you can increase the degree of the polynomials and increase the number of the variables, you realize there's actually going to be infinitely many different questions that you can ask about. I will tell you that the problems change in character a lot once you stop using quadratic polynomials. So let me just mention some polynomials that are of degree higher than 2. A natural one is to look at the pretty symmetry of the Pythagorean one and try raising the exponent. So here is a Diophantine problem to be solved. It also corresponds to a surface in 3-dimensional space. It's a surface that consists of whole lines that go through the origin. But in this case, finding out solutions is much more difficult. You can find some solutions, but they're all pretty boring because they seem to always have a 0 as one of the components. Even if you put a 1 and a -1, then you have a 0 on the other side. In fact, this one has got no solutions, and that was proved by Euler. And the reason that he started doing this was because Fermat had looked at a similar solution, a similar equation rather, like this, that also has no solutions. Fermat came first, which is a little interesting because 4 is bigger than 3. But actually, that's because Fermat had a little trick. What he actually showed is you could never get 2 4th powers adding up to any square, whether that square is actually a 4th power or not. It would always be a square. He found that there's no solutions to that. And he had a very clever argument, but that argument didn't apply to any of these other cases. And Mr. Fermat proposed that we actually look at equations of this type, and he asserted that none of these equations ever had a solution when n is any whole number bigger than 2, unless you do the stupid stuff that I said down here. And he actually even claimed that he had a proof of this. So from his point of view, he had a theorem, but he never actually wrote down a proof. And other people tried to figure out a proof, but they couldn't for a long, long time. And so this became known as Fermat's last theorem. And it was posed in the 17th century. And it was finally proved in the 20th century by, well, Wiles was the person who finally put the nail in the coffin of this one. So it is known that there are no solutions to any of these, but that's actually a much more difficult problem. All right, I actually took a minute longer than I wanted to. I did want to show you one more thing. And this is I want to share my screen with you and show you a web page. Oops, where did it go? Where am I here? How do I share screen? Okay. So this is a little web page about number theory. This is actually something that I made myself some years ago, and it has since gone offline because the person who was maintaining it on his computer had the nerve to pass away. But you can still find it on the Wayback Machine. And I organized it according to the American Mathematical Society's subject classifications for the branches of math. And it shows in particular the different subfields of mathematics, of number theory that you might be interested in. So much of what I talked to you about today was right in here on Diophantine equations, and that included the one I mentioned at the very end as a famous example. Some of these others, you notice that we've discussed these during the semester. So elementary number theory has to do with the modular arithmetic. We did discuss some of these sequences and series. We studied polynomial equations in integers. We didn't do much with matrices. Now, I will mention when I started drawing pictures and looking for points on curves and surfaces, that's actually this branch of number theory. It's a part of algebraic geometry, and it's called arithmetic algebraic geometry to emphasize that we want to find solutions in integers. About some of these other things, let me point out that some of these we have addressed. So additive number theory comes to questions like what numbers can be written as a sum of 2 squares or 3 squares or maybe cubes. How many cubes do you need? That is what's called Waring's problem. Then these categories down here, algebraic number theory, those come to, those are discussions about the kinds of rings that I have been discussing with you, where you take not only the integers, but you adjoin something like the square root of 5, which is the solution of a polynomial equation with integers. So those lead to what are called algebraic number rings and algebraic number fields. And finally, we've had some discussions here about the finite fields. Those are the integers mod p for starters, and some variants of those. But there's just a lot more things that you can do with the finite fields besides the things that we were able to discuss. One more branch of math that I want to point out is this stuff in here. Where did it go? It's analytic number theory. I don't actually see it. Oh, here, yeah, analytic number theory. So this has to do with things like the Riemann hypothesis, which you may have heard of as one of the big unknown questions in mathematics. And you're actually describing, let's say, complex analytic functions like you would see in an analysis class, but you write them down in terms of integers. And then it turns out in some cases, the nature of how those functions behaves will reflect on things that you want to know about integers, like how many primes are there and how far apart are they. So I invite you to explore and to find something else about the different subfields of number theory. Our semester got shortened, and it was already short enough as it was, so we don't really get a chance to delve into all the different parts of number theory, but it's a very fun subject. And if anytime you guys want to pursue some parts of it in more detail, just come drop in and see me sometime in my office, because as you can probably tell, I like this stuff very much. All right, so any final comments or questions that you guys want to make?
So that link, did you put it on your website?
Oh, yes, sure. It's if you go to the Wayback Machine, the website that had that page on it was called the Mathematical Atlas. So you can search for it yourself too. But oh yeah, I'll put a link for you guys up there. Now, just so you know, none of that stuff is going to be on the final, okay? You're not responsible for the zeta functions and for Fermat's last theorem and all the rest of this stuff. I just wanted to whet your appetite so that you come back for more number theory on some future occasion. All right, guys, stick around for my office hours if you have more questions, or come on Monday. I'll have office hours for you. Otherwise, I'll get the final to you by Wednesday morning.
All right, thank you so much.
All right, thank you for being here.
Thank you.
Semester.
Yep, thank you. I'll see you guys.